Okay, so let's start. So I will just first go through some exercise that I didn't complete in the class this week. So first is about Bourgain theorem. We have described the algorithm of Bourgain, which is really just you choose a subset Aij, right? Where for each Aij, you include each element in X, from X into the set with probability 1 over 2 to the j. And then for each of the set, it would correspond to one coordinate of the mapping. That is the mapping of X at coordinate ij is literally the distance from X to the set Aij. So that is the algorithm, like that defines the mapping. So now we would like to say that, okay, actually this mapping can be computed very fast, actually in nonlinear time. Suppose that the metric is defined by a graph with m edges. Then we want to say that the mapping here can be computed in nonlinear time. And the reason is actually, one sec, can I? Yeah, all right. So the reason is, why is that the case? This is because for basically we just want to how to prove this. So the claim is this. So given AI, for given A, actually you can compute dx to A for all x in nonlinear time. Given. And why is that the case? Can someone tell me how to do this? Right. How would you suppose that this is a graph G, and then you define a set A here, and to compute, if you want to compute this for all x, so how would you define a graph? Like okay, so you can create a supersource and connect it to A, right, with weight 0, and then run a single source shortest path like Dijkstra from S, and that would like give you like a single source shortest path. But you can see that the distance from S to T to any node X here is really the distance from X to A. So that is why fixed in A, you can get all distance from A to everyone in X. And now there are just log square many set that you need to do this. So so basically, for given coordinate ij, you can compute the coordinate ij for every node in nonlinear time. Yeah. And there are log square many coordinate, so that's why it's nonlinear. Okay. So that means if the metric is defined by a graph, it's nonlinear. And what if it is general metric? So in the general metric, actually, we can think of any metric actually as a weighted graph. So why is that the case? So given a metric, you can really just create a graph, right, such that any two point, any x and y, you just create an edge with weight that is to be the distance itself. And it's kind of easy to see that if you look at this graph, the distance between any x and y will be exactly the distance defined by the metric, right? So why is that the case? So first of all, good. Like distance in the graph is at most the distance in, like at most the xy for sure, because this is just one path. The NH is a path from x to y. But you would have this the inequality holds in other direction too, and that is because of triangle inequality, right? So for any metric, you can represent it as a graph with n square edges, and so and we already know that given any metric, if a metric is represented by a graph, you can compute f in time proportion, like near linear to number of edges. But any metric can be represented as a graph with n square edges. So that's why you can compute mapping f in n square for any metric too. Okay. And how can I? It doesn't let me change. 1 second. Just okay. So now we know that given a metric, you can compute mapping, Bourgain embedding in nonlinear time. Now I would like to come to this. Why is it the case that we can compute the latent round relaxation of the H expansion fast? So we would like to show this, right? That is, in class we have discussed how to compute the latent round relaxation, which is a log n approximation of H expansion. And now, given what we want, we say that, okay, this algorithm is quite slow because you need to solve LP. And LP in general might not be fast. But modulo that step, suppose that you solve LP and you get which LP is an LP that looks like this. Latent round LP. Once you solve LP and you get the best metric that satisfies this LP, the optimal solution, d-opt. Suppose that you obtain d-opt here. We want to say that, so first of all, if you just want the value of latent round relaxation, once you get, once you solve the LP, then you're done, right? That is just the value of latent round relaxation already. Like you can compute the the value. But what if we want a cut itself? The cut that certify that the cut that have conductance approximately the conductance of the graph. Not just the value of the conductance of the graph, but we want like the cut that certify that the conductance is at most that value. How do we do that? So here we want to say that actually to compute this cut such that the conductance of the cut is approximately the same as like within log n to the conductance or h expansion of a graph, then we can do it in nonlinear time. So how do we do this? Basically, the algorithm actually kind of follow from the proof here. So why is that the case? So suppose that you have, okay, I should. So let me describe the algorithm directly first, maybe. So the algorithm would be given the opt, then compute Bogan embedding, f of the opt. Okay. And once you have f, then you compute the collection of cuts SF such that this is a collection where you know, just like in the class, that this collection basically capture the F, the mapping F for L1 metric. And next is that you just return S such that basically return S in the collection such that is minimized. You really just have a collection of cuts and return the one which have smallest expansion. So do you see that this algorithm, at least the quality of a cut, the expansion of a cut should be good? I mean, this really basically is just from the proof here, right? You have the opt, you compute F. From F, you compute the collection of a cut. And we have here that, like, we just have here that LR of GH is at least this much. So if you just really just look at all the cut in this collection, take the minimum one, then we would know that this thing is at most LRGH times log n. Make sense? And so we know that this is at most log n times LR of GS, which is, but LR of GS is a relaxation. So this is, so the algorithm is correct, but now we just need to argue why we can compute all of this fast. Okay. So first of all, let's look at the easy step here. How fast is the second step? Like given the mapping F, how fast can you compute the collection of cuts? Any idea?
Is the question, how do we get the cut points from the L1?
If the question is how do we compute this collection SF given F, given the mapping F? How fast is the algorithm?
The size of the collection is nearly linear.
Right. So we just basically need to go back to see how come any L1 metric is a collection, like is the same thing as collection of cuts. We just look at the proof there, right? Sorry? Yeah, we follow the proof and see the algorithm. So you have seen that actually, like, given a, maybe I just look at this step, right? If we have discussed in class that if you have a 0-1 line metric, then it is the same thing as the distribution of cut metric, where it is actually a nested cut. So basically given a L1 metric in 0-1 here, you can define, really just sort the point, right, on this interval, and then you define a cut which is basically the first one here, the second one here. The first one should be just this. Yeah. You sort them, and then look at the prefix of this list, and that defines the list of cuts, right? So all you need to do to get this collection of cut is just to sort. Look at the mapping F. Sort them. That's how. Once you sort them, you know all the cut that you want, right? And how would you do it for L1? L1 is just a line metric with many dimensions. So for each dimension, you sort them, sort the points, define the nested cut for that coordinate. Look at the next dimension, sort again, and that defines another collection of cuts, right? So all you need to do is you pay n log n to sort per dimension, right? And how large is the dimension of Bourgain? Log square. So yeah, it's log square. So basically you pay log square times n log n. Yeah. And note that, like when you sort them, log n. Yeah. Where does log n come from?
So now we are sorting only on log square and
They are endpoint. Yeah. Right. So where is my algorithm? Yeah. So to do this, basically you look at F and sort the points for each dimension. So just sort points. Like for each I, sort x with respect to fi of x, right? And that from here you get a nested cut. You get like basically the ith collection where this is a nested cut. Like obtain maybe I call it like the ith one of SF, which is n-1 nested cut. Yeah. And all the cut is just the union of all nested cut for each dimension, log square. Yeah. For dimension I. Okay. And all of this take something like log square times n log n time. Does it make sense? Any question about this? Okay. All right. And for how about this step? Given the metric d opt, you can compute f. So maybe just to make it easy to argue, let me change it to n square. Yeah. Right. But if it is just n squared that we want, then that's fine, right? We just argue about this. Given any metric of endpoint, you can compute Bogan embedding in n squared time. All right. Okay. But all right, how about this? How can we compute this thing fast? So note that if we do it trivially, you have how many cuts? Like near linear number of cuts, n polylog n cuts. And if you just literally just compute the conductance or edge expansion of that cut, given a cut, you read edges around it. That would take something like the size of the graph times the number of cuts. Like each cut you spend linear time. So that is too slow. But actually you can do it much faster. And the reason is that this is not exactly. This is not just some arbitrary set of cuts. These are nested cuts. So suppose that you have this graph, and I have this cut, right? Let's say this is S1, S2, S3, so on, up to SK. My claim is that we can actually compute all of this cut, the edge expansion of all this cut in one scan, basically, by sweep through it, right? Because why? Well, if you want to compute this thing, the edge expansion of this cut, well, here you just spend like just read through all edges here, and you look at the graph H and look at the graph G, and you check how many edges cross the cut in both G and H, right? And you compare them. So this is like, you compare. You compare S1. Yeah. But once you have finished computing the edge expansion of this cut, you can literally just go on to add you can go on and scan nodes in the next cut, right? And then for the edge that actually if there is an edge that actually have endpoint in S1 but have another endpoint in S2, then you discard it from the cut. But if there is an edge that start from S1 but go out of S2 too, then it is still in the cut. But the point is that you just need to scan through, like all you need to do is that you need to look at all the neighbor of the guy in S and like all the edges incident to node in S and decide which of the cut edge that you have found in S1 remain a cut edge for S2. Right. Is this good so far, or this is not clear? Please ask.
Could you actually do it again?
Say it again.
Could you explain the algorithm again? Like I don't understand the part you the edge from S1 goes to outside of S2.
I don't hear the question well.
That long edge. The edge which goes out of S2.
Mm-hmm.
What do you do with it?
Well, if it go out of S2, it is a cut for S2. So that we count it in for that would like contribute to something in this expression. If the edge stop at S2 doesn't go out of S2, we discard it and it will not contribute in the expression here. All right. So what does it mean? It means that if you have a nested cut, set of nested cuts, you can compute all of the edge expansion of all those cuts in just one scan. Spend linear time to compute the compute the edge expansion of all those things. And there are just like log square many collection of nested cuts. So for each of these nested cuts, you spend linear time, and you need to spend linear time for each of the dimension here. So in total, this is actually nonlinear in the number of edges in H, in G, and in H.
So when you have this like kind of long edge from S1 to S3, it will contribute to the cut S2 S3, right?
From S2 to S3? Yes. So that is a new one.
This edge itself, we should update the cut. Like so, if we have a cut from the edge from S1 to SK, we would already update say SK minus 1 to SK cut size. While we are scanning, because we won't return to this edge again.
Okay. So I think maybe it is okay. It seems there are like some questions. Let me be very clear about this step. Okay. So my claim is really this: suppose that you have a cut S here, and if you want to compute, and if you have one more node, U, and let's say S prime is just S union U. So given that you know, suppose that you have computed, if you have computed like the cut of S, then can compute a cut S prime in degree of U time. That's all I'm saying. And The reason is really so you literally just look at you and all the neighbor of you. If this sum of the neighbor, if it is inside S, then you would discard this edge from a cut. And if there is some new neighbor of you that go out of S, that would be a new edge in the cut, right? And to compute a cut in this nested thing, it's really just you repeat this step for every node. And for each node, you spend degree time. So summing up over all nodes is just the number of edges in the graph. Okay. All right. So we maybe I should say that actually given f, then we can compute it in this time. But if you just given d op, I only show how to compute the cut in n square time. So maybe I should say this. So some correction. Given d op, get S in n square time. But if you have the mapping F already, then you can get S in all right, but now, actually, if we want to compute just conductance, you can actually record that for conductance. How does the graph H look like? No, it's not. It's a complete graph where each edge have some weight, right? And this will be so because it's a complete graph. You take something like n squared here, even if H is sparse. And that is maybe not so great. But actually, you can do it quicker if it is just conductance. And the reason is that so why is that the case actually? Why can we compute if I really just return this? If we just want conductance, we can really just return, look at all the cut S in the collection and return the one with minimum conductance. And the total time to do this is still near linear in it will be near linear in number of edges just in G.
Yeah, I guess because the way of clock entries is special is the number, not DU and D.
Right. Yeah.
When you push the content
Exactly. So to keep track of the edge, to keep track of edge cut in G, we do the same trick and spend nonlinear time in number of edges in G. But note that to keep track of, like, what do we want to keep track here? Like, at the end, we don't want to keep track of edge cut in H per se. At the end, this thing, we know that it's approximately the same thing as volume in G of a cut in G. So, and to keep track of the volume of a set is trivial. You have a set S, you add a new node. Just add a degree into the volume. And so that takes linear time. Right? So you don't need to pay the number of edges in H. Okay, so just for conductance. Okay, so now by the way, I would like to clarify one thing about the edge expansion. So like several people asked, and I think it's good to clarify this point. So for edge expansion, you shouldn't think like as if there are like two input. One graph is G, one graph is H, and you want to compute H expansion. You should think of G as your input graph only, actually. And H is just kind of like a problem definition. For example, for conductance, H is something fixed, right? And you measure the volume, you measure the how well the graph H is connected with respect to, how well the graph G is well connected with and how well connected is defined by the graph H. Yeah. All right. So I just would like to finish the exercise here and before going to the next one. So here here I give some more example of metric, and you can just try to verify that these are all metric. But the point is just to say that there are many kinds of metric. And if you have some generic algorithm for metric, like Bogan, it just works for all of these things. But, okay, this is just kind of to recap things in class. So let me denote this L1, the set L1 to be all of endpoint L1 matrix. So it's basically all D such that the axis F where D is for all XY, right? Just all L1 metric. And And actually, I want to prove that the cut cone that we look at in the class, the set of cut cone, this cut cone is exactly the set of all L1 metric. And one direction is actually proved in the class. That is, this is inside cut cone. Why is that the case? Because we have shown that given any L1 metric, it's a combination of a bunch of cuts, non-negative combination of a bunch of cuts. So why is it the case that, can you try to argue that anything in cut cone is in L1 as well? Sorry?
Yeah, because the base of the cut cone is cut metric and it is L1 metric.
Yeah. Yeah. So we have seen that if you choose just one cut metric, that is super special L1 metric is a line metric, right? But anything in cut cone is a sum of cuts, cut metric. So on the other hand, you know that L1 is a sum of line metric. So maybe I should say. So cut metric is line metric. Even like a 0, 1, but doesn't matter. Now, so like this, yeah. And now if you take the thing in cut cone, what is this? This is just a sum of cut metric, right? This is in cut cone. But what is L1? L1 is a sum of lines. So, like, so this thing is a sum of line metric. And so this is in L1. Make sense? Like, you basically take or if you want to create a mapping, for each cut, you create one dimension in L1, in the mapping L1, in the L1 mapping. For each cut, you create a new dimension, basically. Yeah. So this is why you have this too. Okay. And that's why they are really exactly the same. Cut cone and L1 matrix are the same set exactly. So this is like a kind of nice, like one thing is about mapping in the space. Another thing is just a cut, but looks different, but they are exactly the same. Okay, so here I would like to talk about, I would like to motivate a bit about Bourgain algorithm, how to compute Bourgain embedding. Can you simplify it a bit more? And I would like to say that it at least hard to imagine that there is something simpler because of the following discussion. So in class, we already talked about if a graph is a cycle, then something like you can imagine much simpler embedding than Bogan. And the algorithm would be that you choose a random node and random node A, and then for each point X, you just create say that the mapping for X is just a distance from X to A, to that random node A. Okay? And we see that at least in expectation, the distance will be kind of within a constant factor. The difference given any x and y, the difference in the distance from x to a and y to a will be kind of basically the same thing as distance from x to y. And once you have this, then if you want your mapping to be to be with high probability, then you can choose log n different random nodes, right? And so basically the mapping would be the mapping of x would be this a1 a log n and then what would we have? We would have that this thing would be it would be basically in expectation